and Friday I'll return your test and we'll continue with Unit 4. That's the plan, man. Okay. In the meantime, we're going back to look at the atom. So things that we take for granted about an atom, it wasn't always known. So I kind of have some names, some key names, and how it evolved over time, what we know about the atom. So actually, Dalton didn't come up with the concept of an atom, but he kind of brought it up again from, I think it's like Aristotle, like in the BCs, came up with the idea of an entity called an atom. But we attribute Dalton actually coming up with, I think we looked at Dalton's atomic theory back in Unit 1, I think. So that was 1803, but it wasn't until Thomson in 1904 came up with the idea that an atom actually is made up of little pieces that are positively and negatively charged. But it's called the plum pudding version of an atom because they're basically kind of strewn throughout the atom. And then later, Rutherford actually said, no. Basically, you have a hard center, and then kind of that light purple actually is where the electron is, an electron cloud. So Rutherford came up with this idea of the concept of a nucleus, an electron cloud outside. That was in 1911, not that long ago. And then actually we're going to spend some time today talking about what Bohr came up with. So in this picture of Bohr's model, this inside thing here, that's the nucleus. And these actually are electrons that are outside the nucleus in a cloud. Okay, so we'll be talking about that. What Bohr said is that not all electrons are created equal. Actually, electrons have certain energies and they kind of reside in certain locations we call orbitals. Okay, and then there's one more. After Bohr, we kind of took it up a notch and said Schrodinger, kind of the difference here is that Schrodinger said that actually instead of knowing discretely where the electrons are, which looks like Bohr, almost looks like Bohr's electrons kind of orbit the nucleus like planets orbit the sun. No. Schrodinger said electrons have discrete energy states and they are located in discrete regions. So actually Schrodinger, these little black dots, those are all kind of where an electron could be in space around the nucleus. So that's kind of the difference between those. So I have a few more pictures to kind of show you things. This would be Thomson's plum pudding model. He said that there wasn't a nucleus. Basically, atoms kind of had electrons and protons kind of mixed together. He did recognize that if you have, for instance, helium, if you lose an electron, it becomes actually positively charged. Okay, if you lose 2 electrons associated with the helium atom, it becomes positively charged twice, which for those of you who know, it does not make sense for helium to lose its 2 electrons. Okay, so that's Thomson's model. Then on, I think it was Rutherford's model, that has the idea of a nucleus, okay? But the problem here is that it says that we know where the electrons are, and we really don't know where the electrons are. Okay, basically electrons are in a cloud outside the nucleus. But there's this thing called Heisenberg's uncertainty principle, and that actually kind of works in with Schrödinger's model of basically we can know a general region, but we can't know specifically where an electron is. Okay, and then this is on to Bohr's model. So again, we're going to be kind of talking about energy levels today. It's getting sort of echoing. Talking about energy levels today. And what this is showing you is kind of, if we consider this the nucleus, okay, we can consider these electrons being at these different energy levels. Here's an energy level, here's an energy level, here's an energy level. The farther you get out, this is higher energy level, this is lower energy level. Okay, not only are they different in energies, but also they differ with regard to the proximity of the nucleus. So that is true. What we know to be true is that actually you can excite electrons, kind of being shown here. We can excite electrons, and then as electrons fall back down, they emit light, kind of showing here the 2 different options. And I don't talk much about spectra, but here we have the red light is emitted, R for red, and here we have blue, I'll put B for blue. the farther it falls, actually, the higher the energy, and blue is a higher energy than red. So that is Bohr's model. And actually, along the idea of Bohr's model, and we're just going to kind of make an introduction to this today, and follow this up a little bit on Wednesday, then again on Friday, when we talk about finding homes for electrons, is that these are finding homes for electrons. For instance, let's just pick one, shall we? Let's pick the carbon atom. Okay, so here we have carbon. I'm going to pick red. Okay, carbon nucleus has 6 protons. If it's neutral, we need to accommodate 6 electrons. And what this is showing you is kind of in the simplest terms where those 6 electrons are with regard to energy levels. What we call principal energy levels. Okay, so that's what that is. That's the Bohr kind of models. Let's see. I played this video at my office. Let's see if it'll work. Okay. So I think we've looked at this maybe representation of an atom before. So this is an atom. The red and green, the Christmas stuff going on, that's the nucleus of the atom with the different colors are the protons and the neutrons. And then this dot, 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 that's the electrons. Okay, now are there that many electrons? No. But like the animation said, basically we just kind of say a general region where the electrons will be. We call that the electron cloud. Electron clouds are not all spherical. Okay, there's actually some kind of interesting shape depending upon which energy level we're talking about. So kind of back to even the Bohr thing we looked at a little bit ago where we said electrons can be excited, electrons can fall back down and emit energy. The energy of an electron has discrete possibilities. We call that quantized. And so like usually when I'm talking about it, like I'm putting my hands like this, and as I put my hands up or down, I'm really kind of having imaginary y-axis. Okay, so where basically we have energy, and so energy increases as you go up, and it decreases as you go down. So these are just different energy levels. Okay, that's when my hand is. So we call that quantized. So when we talk about any sort of quantized, if a value is quantized, it means it can be, you know, here or there, but it can't be something like a continuum in between. So I have an example of 2 possibilities. If we're talking about the elevation that this chemist can be in, this can't be drawn to scale because basically these stairs are about up to the dude's hip, which is kind of strange. The other thing is who walks around with a beaker like this? But anyway, the point is if we're talking about the chemist's elevation, can you see where on steps he can be here, he can be there, he can be there. That's quantized. On a ramp, not quantized. So that's all that means. Okay, so we deal a lot in here with electrons as they are in a cloud outside the nucleus of their atom, as the electrons are residing in what we call their ground state. Their ground state. That's the lowest possible energy for that particular set of electrons. So we looked at carbon a minute ago that had like 2 electrons and 4 electrons. In their ground state, they are all, and I kind of go like this, like I'm near the nucleus, I'm at the lowest energy possible. Okay, ground state electrons. Of course, opposite of ground state would be excited state. Okay, and that happens a lot around us. A very common way electrons are excited is when you turn on a light bulb. Basically, you have a gas in that light bulb, and electricity is, in particular, exciting the electrons to go to a higher state. As they fall back down, they emit light. Okay, so it happens a lot. Fireworks, common example of electrons being excited as they fall back down, they emit those beautiful colors. Okay. So electron orbital, I kind of feel like we've talked a little bit about that. Electron orbital is where the electrons are hanging out. And we're going to see that there are some rules about electron orbitals. The thing about electron orbitals is they will have a specific space about the nucleus. The nucleus will be at the center of an electron orbital. And electron orbitals have specific shapes. Electron orbitals have specific energies. Okay? So electron orbital, where in general an electron will be. I know this says 95% probability. So it ends up being kind of like this bell curve, sort of the probability of finding an electron in that location. Okay, so we're going to come up with some rules about how electrons hang out in their ground state around the nuclei of their atoms. How do electrons hang out? So electrons are located in orbitals. An orbital can only have 2 electrons. And if 2 electrons are in that orbital, those 2 electrons must have opposite spins. So I'm going to start to kind of throw some things at you. You may have seen before, you may not have. But orbitals, it works real well. Anytime orbitals in here, oftentimes will be drawn with a box. That is my orbital. And I think what works well, and I guess I'll choose red, what works well is to use arrows for electrons. So here we go. Here's 1 electron in that orbital. This is an orbital. Anytime you see boxes. That's 1 electron. This says, and we'll be talking more about spins coming up, okay? But if you want to visually show a 2nd electron in that orbital with an opposite spin, then you just make it go the other direction. Okay, so the box is an orbital, the arrows are electrons. Sometimes instead of a box, it's more convenient just to draw a line, okay, as 1 orbital, okay, and then again, if I am accommodating 2 electrons in that 1 orbital, they must have opposite spins, okay? So there you go. And a lot of times I'll just make the arrow with just a half a thing. So orbitals, that's kind of an idea of an orbital. So orbitals are going to be organized into what we call subshells. Let me show you kind of our first interesting subshell of orbitals. And this might be ringing some bells for some of you. Sometimes I lose some students here because they're like, I've already seen that. But just pay attention because you might see something you don't know. Okay, there is this cool type of subshell called P, and it actually has, guess what, 3 orbitals. They are all at the same energy, okay? So let's go ahead and fill up that subshell. That's what we call, this is a subshell. I'm going to fill it up just because I can. They're not always filled up, but I did. So P-type subshell. So what we're going to see is that orbitals that are the ultimate homes for electrons, okay, are actually organized in subshells. And I just kind of showed you a P-type there. But this goes on to say, and we're going to use the word degenerate here in a minute, but if you do have orbitals in the same subshell, they are all degenerate, and they have the same energy. The last thing with regard to organization is that subshells are organized into what we call principal energy levels, or energy levels. You heard me use the word principal energy levels, right? Okay. To give you an example of that, and we'll be talking more about this, but I guess where it gets maybe more interesting, let's pick a principal energy level. N, that's my principal energy level. N is equal to 3. Let's just for kicks do that. We actually, and I'm going to do it in order of increasing energy. We actually have a 3s subshell, a 3p subshell, and a 3d subshell. Just for kicks, and you're going to see this later, but I'm going to put 1 orbital in my 3s subshell. Guess what? I'm going to put 3 orbitals in my 3p subshell. Those are terrible boxes. And I'm going to put 5 boxes or 5 orbitals in my 3d subshell. I'm just kind of giving you a taste of what we're going to be talking about, or what we're talking about. As these are listed in terms of orbitals, subshells, and principal energy levels, they are actually in order of decreasing specificity, or more general as you go down here, more specific as you go up. So that's kind of what we're talking about. And each box, again, can only accommodate, each box is an orbital, can only accommodate 2 electrons. If it is accommodating 2 electrons, they need to have opposite spins. So I mentioned Heisenberg's uncertainty principle, and that kind of, to me, gets us to the concept of an electron cloud. You'd never know exactly the location and the energy that an electron will have around a given atom. I've heard it described a couple different ways. One is that if you are lucky enough to locate it, bottom line, to locate it, you have had to add energy to it, so you can't both locate it and know its energy at the same time. I've also heard that Heisenberg's uncertainty principle applies to very small things like electrons. So it's not just the uncertainty associated with the location and position, or the location and energy of an electron. All right, so it's all about electrons right now. We're kind of honing in on the electrons. Their energy is quantized. We need to ultimately say what energy those set of electrons, for instance, around a carbon atom have, those 6 electrons. Well, we're going to use quantum numbers to basically, a set of quantum numbers to look at each electron. Now, we aren't going to look at it, but we can identify each electron and give it a set of 4 quantum numbers. And they're going to act like a zip code. Okay, so for instance, these actually are the 4 quantum numbers. It's like a, you know how if you have like an XY coordinates for something? This is XY, this is, oh, I run out of Z, right? X, Y, Z, and B, or whatever. It's like a set of kind of an ordered pair that you give for an electron. For instance, with regard to the energy that an electron has, what is the principal energy level it's hanging out in? That's going to actually be the variable n. Then getting a little more specific, what is its angular momentum quantum number? Now here's where, if you've had this in high school, sometimes they don't use the same terminology as I do, or as probably if you're sticking on, you know, if you're going further into science, what you need to know. That S, P, D, and F, for instance, that actually is what we call the, associated with the angular momentum quantum number, L, the variable L. Even a little more specific is what I say, what box it's in, which box in a particular subshell it's in, and that's the magnetic quantum number, M sub L. And last but not least is the spin number, M sub S. Okay. So this is actually, this topic, it's almost easier to kind of show you how it works than to describe it to you. But if N is the most general and M sub S is the most specific, okay, we could say that like N is the state, okay, the angular momentum quantum number, that's actually going to be the subshell type is the city, or subshell is the city. The specific box or orbital, that's going to be the street. And whether it's got spinning up, because when I told you about spin, all I've said is I've kind of drawn an arrow up and I've drawn an arrow down. We're going to see that the spin number only has 2 possibilities, up or down. It's +1 or -1, +1/2 or -1/2. And 2 possibilities for that last one. So when you work problems, actually for each electron, there's a value for each one of these 4 things for that electron. So each quantum number has rules that goes along with it, and let's see, how do I say it? I guess they have rules that go along with it. They have specific kind of book rules that go along with it. Then to me they have kind of an overarching, well, that's how that works sort of thing, okay? So the principal energy level N, its rule is this. Basically it needs to be an integer, and it can be anywhere from 1 to infinity. That's the principal energy level. Because remember we said that actually we're going to be worried about electrons as they are in their ground state. Well, I could put my hand clear up here, and that's a high principal energy level. We make a side electron up there. Okay. Okay. So principal energy level, N. So the deal about that is, and it's kind of like I've been showing you already, the lower the principal energy level, not only does it have less energy, but it's closer to the nucleus. Okay? As we talk about higher principal energy levels, they get further from the nucleus and they have more energy. So here's a good one, helpful one for you, and I will remind this about you later. Actually, in the periodic table, we learned that the rows are periods. Okay, these are periods. We said you know the period number if you look kind of on the edge of the periodic table. And the black and white ones I gave you for your tests have it, and so does this. So for instance, I'm just looking at rubidium here. Rubidium is in period number 5, period 5. Okay, and when we're finding homes for electrons around rubidium, so for instance, rubidium has 37 protons, so we're going to find homes for 37 electrons. What you're going to see actually is that the valence electrons are going to peter out at principal energy level N is equal to 5. So actually we're going to call this 5s1, and I'll be talking about that. But that's kind of a helpful thing. All right. So angular momentum quantum numbers. If you want to put subshell, you can, because that's kind of what we're talking about. Subshell. And some of you, and I have a slide coming up here to kind of correlate these. But if you're like me, you learned them in high school as we have different types of subshell. We have the S-type subshell. We have the P-type subshell. We have the D. And we have the F, and actually we have beyond that too, but those 4 are all we got to worry about if the electrons are in their ground state. As I've drawn them, and actually it's coming up, but they map, I've just used that word for the first time this semester. An S-type maps to an L value of 0, a P-type maps to an L value of 1, a D-type maps to an L value of 2, an F-type maps to an L value of 3. And you might be like, well, why do we have to map it to anything? Why can't we just say S, P, D, and F? Because that's not the way it works. And actually, once we convert it to a number, then there are other options. Okay. So notice for a given principal energy level N, your options, your only options for L, only possible L values, they have to be integers. And they are going to be integers starting at 0 all the way up to n minus 1. N minus 1. So a minute ago, when I picked on n is equal to 3, check this out. If n is equal to 3, notice I bump up at 3 minus 1. The biggest L value I can have is 3 minus 1 is 2. So all of my angular momentum quantum numbers options are being 0, 1, and 2. That's exactly what I drew. I drew a 3s, a 3p, and a 3d. So that's kind of how that all works. So again, what's with the mapping? So you may have learned it as S, an S-type subshell, or an S-type subshell holding orbitals. The value of L is 0. You have P-type orbitals in a P-type subshell. The value of L is 1. D, the value of L is 2. F, the value of L is 3. So all of these other ones actually, N is, sorry, not N, L is equal to 4 and 5 correspond to a G and an H-type subshell. Okay, those actually are up here. Those we don't actually, as we're finding homes for electrons, you can pick the most complicated atom there, okay, and we won't be populating these types of subshells. All right, that's exactly what this is saying. So somewhere, probably, it's going to be helpful for you to kind of make the connection between S, P, D, and F of L is equal to 0, 1, 2, and 3, I think. Okay. So actually, I talked about this a minute ago, I think, when I picked a P-type let's just go ahead and pick, let's pick on the principal energy level is N is equal to 3, and you can actually have a 0, 1, and 2. Let's go ahead and pick on 3p, and I'm going to go ahead and make an energy diagram. So they're all at this energy, and I'm going to go ahead and just, I won't make them boxes, I'll make them lines this time. Any p-type subshell has 3 p orbitals. So actually each one of these orbitals, okay, all have the same energy. That's all it's saying. The word we use for that, and I mentioned it before, sounds like a bad word, but it's really a happy word, is degenerate. Okay, so this is actually, you're along the y-axis, basically you have energy, and you have several boxes or several orbitals at the same energy because they're in the same subshell. Specifically the same subshell type with the same principal energy level. Degenerate. Okay, so I've got a couple slides here to kind of get you used to thinking. The 2 quantum numbers we talked about was the principal energy level, okay, and then the subshell type, okay. So principal energy level, N is equal to 1, only has one possibility, okay. And this seems a little scrambled to me. I was looking at this at my office. So usually what I'll end up doing is making an onion. This is increasing energy as you go up, okay, and this would be the lowest energy. So basically you have N is equal to 1, you have one possibility, 1s, N is equal to 2, you have 2s, 2p, N is equal to 3, you have 3s, 3p, see how I'm going up, 3d, and actually I'm going to have to do some kind of unscrambling here when N is equal to 4, but just for kicks, I'll go ahead. On the next slide, N is equal to 4, you add the option of 4f. So here you have 4s, 4p, 4d, and 4f. So that's kind of what we'll have going on. But like I said, don't forget that to be able to say intelligibly what the L value is from the SPD or F. So there are rules, and it's kind of what I feel like I'm kind of repeating myself a little bit, okay? So when you have the principal energy level N set, N can be anything from 1 to infinity. When you have that set, when you look at the subshells that are possible, it's values of 0 up to N minus 1. So it does have an upper limit. So I feel like I'm repeating myself. So when N is equal to 1, you have values of 0 all the way up to 1 minus 1, and 1 minus 1 is 0. So that's why basically you only have one option for the angular momentum quantum number. When N is equal to 2, you have possible values for L of 0 all the way up to 2 minus 1, which is 1. So your only options are L is equal to 0 and L is equal to 1. When N is equal to 3, you can have L values of 0, 1, and 2. When N is equal to 4, you can have L values of 0, 1, 2, 3. When N is equal to 5, you can have values of L is equal to 0, 1, 2, 3, 4. Okay. Exactly like I said. And this again is kind of summarizing again the different types of subshells you can have at those principal energy levels. Just a different way to look at it. Okay. So a little bit ago, when I kind of, in a black pen, I wrote 1s, and then I wrote 2s, 2p, and then I wrote 3s, 3p, 3d. I was careful that as I went up in energy, I always wrote the lowest energy is the S-type subshell within that principal energy level, and that's all this is saying. All right. So now this would be which box. To me, this is like which box. Remember, box is an orbital. So this is which orbital amongst those possible degenerate orbitals is an electron going to be at? Or is it at? Let's give it a quantum number, okay? So to me, it's easier to look at than to actually what the number is. So here's all it means. Let's pick on P again. Let's pick on 3P, shall we? Here we go. Principal energy level N is equal to 3. We know it can have a P-type subshell, so P, the L value would be 1, right? Okay, so that L value is 1. So let's go ahead, and I'm going to go ahead and draw 3 orbitals here. Now, this M sub L value, okay, we said that because it's a P-type, we said that means L is equal to 1, right? Okay. So M sub L values, possible M sub L values are 0 all the way up to plus or minus L. So if L is equal to 1, all I got seems like kind of a dead end. My M sub L values possibilities here for any P-type subshell is 0 plus or minus 1. That's it. I'm going to go ahead and expand that out. M sub L is equal to minus 1, 0, or plus 1 for any P-type subshell because L is equal to 1. So all I'm going to do is to take these numbers and I'm going to throw them up underneath these boxes. And I'm going to say the M sub L value for this first one. You might be, well, why is it the first one? Well, because it's the easiest. M sub L value for this box, this orbital, is minus 1. The M sub value for this box is 0. The M sub value for this box, M sub L value for this box is plus 1. That's it. That's all I'm talking about. So just for kicks, I'm going to put only one electron in that first box. Here we go. Here's my one lone electron. Here's my arrow in that first box. So this is all to say that I could say what the zip code is for this electron. Okay, and it usually goes N, L, M sub L, M sub S. That's what my zip code coordinates are. So here we go. I told you, what's my N value? You guys tell me. What's my N value here? It is 3. That is my N value. It's 3. That's the principal energy level. What's my L value? 1. It is just 1. Very good. What's my M sub L value?
Plus 1.
I stuck it in this one.
No,
Minus 1. Yep. Perfect. And then the last one we haven't talked about, but if it's pointing up, it's plus 1/2. Pointing up is plus 1/2, pointing down is minus 1/2. So I'm going to go ahead, my M sub S value is plus 1/2. That's it. That's all it is. That set of quantum numbers identifies that electron right there. You might be like, could you make it any more difficult? No. Okay. So M sub L, okay, the M sub L value is actually which box, which orbital in a given subshell. And values of M sub L are driven by the value of the L. So it's 0 all the way up to plus or minus the value for the L. So I haven't picked on S. I've picked on P a lot. Every time I had a P, you saw me put up 3 boxes every time I had a P. And now maybe you know why, because those 3 boxes correspond to M sub L values of minus 1, 0, and plus 1. Anytime I put it up an S subshell, it can only have 1 orbital. That's it, 1 orbital. And the M sub L value is 0. That's it, okay? Any P-type subshell, it's what I've been kind of putting up. Okay, you actually have 3 boxes, 3 possibilities for M sub L values, minus 1, 0, and plus 1. And it does seem a little arbitrary, like, where did that 1 electron go? You could be a rebel, I guess, and say it went to the plus 1. which I think it probably could. So anytime you see a p-type subshell, it's going to have 3 orbitals, and those are the m sub l values. And it's all about oddsies. So we went 0, 3, and then the pattern would be 5. So if we go to an L is equal to 2, a D-type subshell, L is equal to 2, D-type subshell, we definitely have 5 boxes. And underneath those 5 boxes, if you wanted to put m sub l values, you'd put, and I think it's so symmetrical, it'd be -2, -1, 0, +1, +2. And last but not least, to accommodate electrons in their ground state around any atom known to date, would be an F-type subshell. So F-type, we said maps to an L value of 3. We said that M sub L values are always going to be, your allowed values for M sub L in a given L are 0, ±1, plus or minus, all the way up to plus or minus L, which, if L is equal to 2, plus or minus R. Yeah, oops, sorry. Plus or minus, L is equal to 3, plus or minus 3. There we go. So I'm going to draw out this last one. Now, Mr.
I always wanted to do that.
So, I haven't drawn an F-type subshell, but here we go. And you don't get an F-type until you get into the 4th principal energy level. So 4th and anything above, then you get your F-type subshell. So let me pick on 4F, just to kind of remind you how this goes. I'm going to go ahead and draw 7 boxes. These will be my orbitals. These will be where I can accommodate 2 electrons each. There's my 7 orbitals. And I'm going to go ahead and take these m sub l values and apply them underneath. If you're a visual person, this is kind of how I think of it. So I'm going to go -3, -2, -1, 0, +1, +2, +3. And you might be, do I need to add the plus in front of the +1 or +2? No, probably not. But I usually do. Okay, so that's kind of how that goes. So let's go ahead and put an electron, just because we can. Let's put an electron in that first box. 1 electron in there, and we'll have it pointed up again. So, again, and this is kind of how your homework goes. Come up with that purple electron, the principal energy level N. Let's see, the L value, the M sub L, and the M sub S. Okay. So here we go. What is the N value? It is 4. Very good. And the L value? 3. Perfect. 3 because it's F, right? I'm liking that. And M sub L? -3. Perfect. And then what did I tell you if it's spinning up or if it's pointed up? That's +1/2. Yep. Yep. That's exactly it. That's it. Okay. I think that's a good place to stop for now. Very good. So we'll start on this slide and kind of remind ourselves what we talked about today on Wednesday. No homework due. Oh my gosh. But we'll get to that last assignment slide on Wednesday that will be due Friday.